All right, for our next talk, we have Stephen Landsburg. He is an American professor of economics at the University of Rochester in Rochester, New York. From 1989 to 1995, he taught at Colorado State University. Landsburg is also an outspoken commentator on economic, legal, and political issues. Here's Truth, Provability, and the Fabric of the Universe by Stephen Landsburg.
Oh, you might have heard, is the sound okay? You might have heard about the famous foot race between Achilles and the tortoise that took place about 3,000 years ago. Achilles was faster, but the tortoise had a head start. And that was fatal to Achilles because in order to win the race, he had to first close half the gap between himself and the tortoise, and then he had to close half the remaining gap, and then he had to close half the remaining gap, and then he had to close half the remaining gap. And that was an infinite number of steps, which was beyond his capabilities, so Achilles lost the race. 19th century calculus explains pretty clearly why Achilles really ought to be able to cover those infinitely many steps in a finite amount of time, but this took place 3,000 years before the 19th century, and so he was doomed. Now, what's less well known is what happened after the race. We know this on the authority of the historian Lewis Carroll, who tells us that after the race was over, Achilles and the tortoise sat down to do some math. And Achilles says, I'm gonna prove some theorems for you. First, I'm gonna write down an axiom. And my axiom is, two things that are equal to a third thing are equal to each other. And the tortoise sort of looked at that and scratched its head a little and said, that makes sense, I believe that. That's a good axiom, I like that. And then Achilles drew a little triangle in the sand and labeled the sides and said, my next axiom is that sides A and B of this triangle are both equal to side C. And the tortoise pondered that a little bit and said, that makes sense too. I like that axiom. Achilles said, now I'm going to show you how to reach a conclusion. The conclusion is that sides A and B are equal to each other. And the tortoise said, no, I don't buy it. Doesn't make sense. And Achilles said, wait a minute, maybe you don't understand what we've just agreed on. We agreed that if two things are equal to a third thing, then they're equal to each other. And the tortoise said, yeah. And we agreed that A and B are both equal to C, yeah. And Achilles said, but if you accept A and you accept B, then you've got to accept the conclusion. And the tortoise said, oh, is that an axiom? And Achilles said, well, yeah, I guess so. And the tortoise said, well, you better write it down then. So Achilles wrote down his axiom. If you accept A and B, you must accept the conclusion. And the tortoise looked at it and said, yeah, I agree with that axiom. That's true. That's true. Achilles said, great, then you accept the conclusion now. Tortoise said, no. Achilles said, but if you accept A and B and C, then you got to accept the conclusion. And the tortoise said, oh, is that an axiom? So Achilles wrote that one down. And, 20th century logic with its very clear distinction between axioms on the one hand and rules of inference on the other would have saved Achilles, but this was long before the 20th century. And so he went down to his second defeat of the day. Let's put that story aside in our minds. I'm going to come back to it much later. And let's jump forward to Richard Dawkins. Richard Dawkins, I assume, is familiar to almost everyone in this room. He is, to my mind, an international treasure. He wrote a book called The Selfish Gene, which, if you've never read it, is one of the best books, I believe, ever written. And Richard Dawkins, on one occasion, said, this is a direct quote, Darwin made it possible to be an intellectually fulfilled atheist. Now, what did he mean by that? What he meant was, and this is all quote from Dawkins, is that before Darwin, you could have said, well, I have no idea where all this complexity came from. But God does not seem like a good explanation. On the other hand, I have to admit I don't have a better one. And Dawkins says, I can't help feeling that would have left one feeling pretty unsatisfied, but that's where we would have been if it weren't for Darwin. It would have been logically possible to be an atheist, but it would have been frustrating because we would have had no explanation for this big thing. Or to put that another way, the world is full of very complicated things like anthills and whales and human brains. And the question that Dawkins is addressing here is, how do you get from much simpler things to these complicated things? How do you get from, say, krill to whales? Well, krill is a lot less complicated than a whale, but it's still pretty complicated. So maybe we should push that back a little further and ask, how do you get from clay to krill? Or how do you get from organic modules to krill? And Darwin did a pretty good job of setting us on the path to answering those questions too. How you get from simplicity to complexity, and Darwin's successors have pushed that back farther and farther and explained how you get from very elementary non-organic material to living material, and then from there to more and more complex living material. That's great. But I don't think it makes it any easier to be an intellectually fulfilled atheist, because it leaves completely open the question of where did the krill and the molecules come from. In other words, if you're thinking about how did we get to something as complicated as a whale, Darwin kind of filled in how you get to whales once you've got something. The much longer intellectual journey, it seems to me, is how do you get from having nothing at all to having the raw building blocks of whales or anything else. And I am afraid that we are in as much of a intellectually unfulfilled state with regard to that as Dawkins imagines we were before Darwin. So I think Dawkins has sort of pointed to the wrong thing here. Darwin closed the gap toward intellectual fulfillment a little bit, and that's fantastic, but it's only a little bit of the gap. The bigger question was the one that was famously raised by Leibniz in the 17th century: why is there something instead of nothing? And I think if you can't answer that, and who can, then there is this intellectual tension. There's this feeling that there's something that we wish we understood, and God doesn't seem like the right answer, but what does seem like the right answer? Maybe there is no answer. Okay? Maybe there just is stuff, and that's all there is to say, and there's no reason beyond that. But that seems kind of intellectually unfulfilled. So I would like to suggest a story about how we get from nothing to something. I'm not sure it's the right story, but it's a story that, to me, has a chance of being right, and I don't know any other story that has a chance of being right. It's a story that's going to take a little bit of explanation. It comes in a couple of parts, and each part, I think, if you have not seen this kind of argument before, is going to sound very mysterious and like you're not even sure what it means, let alone how it could be true. But bear with me. I'm going to state the two parts of the argument, and then I'm going to come back and try to clarify what they mean. So here's my possible answer. First of all, mathematical objects exist. What's a mathematical object? The Euclidean plane, the plane that you studied in high school geometry, containing all of its lines and points and angles. That's a mathematical object. It's a mathematical object. It is just defined by its properties. The natural numbers, the counting numbers that you learned about when you were 3, 0, 1, 2, 3, 4, not just the individual numbers, but the whole system of numbers and the ways in which they interact with each other, the ways they divide each other, the ways they add up to each other. That's an example of a mathematical object. And I want to argue that those things, that it is possible to understand why those things exist, and that they do exist, and that they exist in exactly the same sense that cockroaches exist, and rocks exist, and trees exist, and your brain exists. And again, if that sounds a little strange and implausible, please bear with me, I'll come back to it. And then the second part of the argument is going to be that once you've got something existing, you've closed the gap, you're done. Nothing else exists, so there's nothing else to explain. Everything else is made out of mathematics. Everything else doesn't appear to be. I look around, you don't look like a mathematical object, but that's partly because my senses evolved to perceive you as something very different than what you really are. Everything else is a mathematical object, and once we understand why mathematical objects have to exist, then we've we've solved our problem. Again, am I going to prove to you this is right? Absolutely not. What I hope to prove to you is that a reasonable person could believe these things, or that a reasonable person could believe that these things are possible. And again, I have no other story that fills in that gap between nothing and something. So let's start with the first part. Mathematical objects must exist. Before we can address what that means or why you might believe it, we have to address, what does the word exist mean? What does it mean for something to exist? The answer that you will most often get from the philosophers is that a thing exists if it has properties, if statements about that thing are objectively either true or false. A unicorn, for example, does not exist, and the Wisconsin State Capitol does. Why? Because if I ask the question, does every unicorn have a blue stripe, there is no right or wrong answer to that question. There is no such thing as the objectively right or wrong answer to that question. The fact that questions about unicorns don't have objective answers is exactly what it means for them to not exist. If I ask, was the Capitol built in 1917, you don't need to know what the answer to that is. All you have to do is believe that it has an answer, that there is a right or a wrong answer to that. And as long as you believe that, that's evidence that the Capitol does exist. So on that basis, I want to draw what I hope is the uncontroversial conclusion that the Capitol exists and the unicorn doesn't. And by that standard, how do, say, the natural numbers stack up? Do the natural numbers exist? Well, here are some questions about the natural numbers. Are there infinitely many prime numbers? That's a question we could ask, just like we could ask, was the Capitol built in 1917? Does a unicorn have a blue stripe? Is every natural number a sum of 4 squares? Is every natural number a sum of 2 primes? Here are the answers to those questions. Yes, there are infinitely many prime numbers. Euclid knew that 2,000 years ago, and he knew why. Is every natural number a sum of at most 4 squares? We've known that for a couple of hundred years, thanks to a guy named Lagrange. To be clear on what that means, it means if you give me a number like 938, and if I think long enough, I will be able to find 4 squares that add up to that number. 938, you can check on your calculator if you're obsessive, is equal to the sum of these 4 squares. Is every even natural number a sum of 2 primes? You give me an even number, can I write it as a sum of 2 primes? I don't know, nobody knows. Okay? There are people trying to figure that out. Pardon me? Every even number greater than 2, thank you. Is every even number greater than 2 a sum of 2 primes? I don't know the answer to that. Or I could have asked the question as it's stated there, and then I shouldn't have written to no, I should have said no, because 2 is not a sum of 2 primes. The point here is you don't need to know the answers to these questions for my argument. All you have to do is believe that these questions have answers, and that the answers are objective, and that there's no matter of opinion here. There's no subjectivity. These questions have answers. I want to stress also that these are statements about the entire set of natural numbers, not about any individual number. And I say that to head off the occasional person who has this strange philosophy where he says that I believe that individual numbers exist, but I don't believe the set of all numbers exists. There are people who say, yes, I believe in 938, I believe in 939, I believe in 940, but I don't believe that all numbers exist at once, because an infinite number of things can't exist at once. It's a strange view, but there are people who have that view. I want to point out that this addresses that view. These are not, when I say every natural number, a sum of at most 4 squares, I'm not talking about one number, I'm talking about all of them at the same time. So these are statements about the entire set of natural numbers, and I take these as indicative that that set exists. So here I have my unicorn, here I have my Washington State Capitol, and here I have, that's the way mathematicians denote the set of natural numbers, the big N with the extra bar on the left. The unicorn doesn't exist, the other 2 do, and I think I've given the criteria by which that's the case. Now, an alternative story. Okay? Some people will say to you, oh no, those are not objective facts. Every number is a sum of 4 squares. That's just something that followed from a bunch of arbitrary axioms that somebody wrote down. That's what mathematicians do. They write down a bunch of axioms, they derive consequences, And that's what you did here, but you weren't actually talking about a real thing. And if it weren't for humans, there would be no axioms, there'd be no math. Math is invented by humans, according to this view. The world can't be made out of math because humans can't be made out of math because math's made out of humans. That would be the argument I want to respond to now. In order to respond to that story, you have to understand something about how mathematicians use axioms. And you have to understand that axioms are used in mathematics in two very, very different ways. Here's the first way. An axiom is an assumption for the sake of argument. So here's this way of using axioms. Here are my axioms. All Jabberwocks are Toves, all Toves are sliding. I don't make any statement about what a Jabberwock is, what a Tove is. There's no meaning attached to these words. They're axioms about meaningless words. And then I apply my rules of logic and I conclude that all Jabberwocks are sliding. That's one way of using axioms. You don't pretend they mean anything, but you still can draw conclusions from them, and that's useful because once you've done that, then you can start interpreting your argument by assigning different meanings to the words. For example, everywhere you see the word Jabberwock, you could cross it out and put women, and wherever you see Tove, you can put human, wherever you see slide, you write mortal, and then if you believe those two axioms are true, you believe the conclusion is true. Or you could put in gorillas and primates and mammals. Why is this a useful thing to do? Because a lot of arguments are not just 2 lines long. A lot of arguments are thousands of lines long. And if you make that argument, you start with 2 axioms, and then after thousands of lines, you get to a conclusion. That's really useful because then when you want to take a specific case like this, you don't want to go through your thousands of lines again. You want to say, all right, I already did that reasoning. Now I'm just going to plug in the substitutions and get my interpretation. When you're using axioms this way, you really want them to have lots and lots of interpretations. The more interpretations they have, the more useful they are. But there's a second way to use axioms. That was the axiom as an assumption for the sake of argument. A different way that mathematicians use axioms is by treating them as self-evident truths about a particular thing. This is more in the spirit of the way Euclid used axioms, when he said that through any 2 points there's one line, through any 2 lines meet in at most one point. He wasn't planning to look for many, many different interpretations of these things. He was trying to describe an object that he believed already existed, and that was the plane. When we use axioms that way, we're often rooting for there to be just one interpretation because we want our axioms to describe that thing completely and uniquely. If they applied to something else, then they would not have done their job of telling us what is it that makes the plane different from every other thing. We're using the axioms to tell us what makes this thing different from all other things. We want there to be just one interpretation. This is in particular true over the last century. There's been a lot of work starting about the year 1900 on axiomatizing arithmetic. And when mathematicians think about axiomatizing arithmetic, they're using axioms in that second sense. They're looking for a set of axioms that are self-evidently true about the natural numbers and not at all true about anything else. Not all true about anything else. This is a guy named Giuseppe Peano, who a bit over 100 years ago came up with the axioms that are now absolutely standard in mathematics for working with the natural numbers. I'm not going to go through every one of them, but you can see the flavor of them. 0 is a number. Every number has that's plausible, right? Every number has a successor. The successor of 3 is 4. No 2 numbers have the same successor. Then there's an infinite number of others. If there are any even numbers, there's a smallest even number. If there are any primes, there's a smallest prime. Any statement of that grammatical form is also an axiom. So there are actually an infinite number of axioms here. Doesn't matter what they specifically are. The point is that these are the standard axioms that we take as the basis for doing arithmetic. Ideally, all of these axioms would be true about the natural numbers, and the natural numbers would be the only thing that they're true about. Model means interpretation. The natural numbers should be the only interpretation. We want these axioms to define the natural numbers, to tell us how they're different from everything else. Forget it. This is a guy named Kurt Gödel, who in the 1930s showed that you can forget about 2 and 3. The axioms that Peano wrote down apply to the natural numbers, but they apply to a great many other systems of numbers as well, other than the natural numbers we all grew up with. The Peano axioms have multiple interpretations, and one consequence of that is that there are true statements about the natural numbers that can't be proved from the Peano axioms. So the Peano axioms cannot be giving us a full description of the natural numbers. There are true statements about arithmetic that can't be proved from these axioms. They can't be a full description. That's just the tip of the iceberg. The deeper fact is, no system of axioms will do what Peano wanted to do. What Gödel proved is that there is no system of axioms that can prove all the true statements in arithmetic. Any system of axioms you write down about arithmetic will be incomplete in the sense it will not fully describe the natural numbers. There will be true statements about the natural numbers that can't be derived from their axioms. What's an example? Now, when I say that, that sounds very abstract. I want to give you an example of a true statement, an explicit example of a true statement about the natural numbers that can't be proven. We started with Achilles. Now I'll go to my second strongman of the day, Hercules. Hercules, as you may know, killed his wife and children and therefore had to do penance by completing a bunch of very difficult tasks. The first one was to kill the Nemean lion, which he did with his bare hands. And his next one was to fight the Hydra. And that was a much harder task because these are two different hydras here. A hydra is a creature that's got heads growing out of heads growing out of heads. And Hercules' problem was that every time he chopped a head off the hydra, a new head grew back. Well, I'm here to tell you it was actually far worse than that. Here's Hercules, and here's the hydra he was going to fight. I don't know it was this particular hydra. It might have been a more complicated one. But let's suppose it's that one, and I've put letters on the heads there so that I can talk about them. Here's what happened. Hercules came along with his sword, and he gets to cut off any one of the top heads that he wants to. He can't cut down here. He's got to cut off one of the top heads. So he gets to choose. Let's suppose he happens to choose head C. He cuts that off. It's gone. The old Greek texts tell us that the head grew back. Okay? But I'm going to tell you something far worse happened. The Hydra looks at the cut off head, goes back to that head's grandfather. I'll call B the father and A the grandfather, and then reproduces everything above the grandfather. In this case, the grandfather is the very bottom of the tree. And everything above that, B, D, E, F, G, H, all gets reproduced. Now Hercules gets to cut off another head, any top head that he wants to. Maybe he picks the red F. Cuts off the red F, it's gone. The Hydra goes back to the grandfather. E is the father, B is the grandfather. What sits above that is D and E. The Hydra reproduces that, not once, but twice. And on the third round, the Hydra says, go ahead and cut off a head, but I'm going to go back to its grandfather and reproduce everything above that grandfather 3 times. And then cut off a head, I'll go back to its grandfather, and I'll reproduce everything above that 4 times. The question is, things seem to be getting worse and worse and worse. Can Hercules turn this around and eventually start cutting this Hydra down to size, all the way down to where he's cut off all its heads? Can he win? I'm going to tell you 3 increasingly surprising things. First of all, if he's really smart, he can win. That should surprise you if you understand the game. Okay? It's really, it seems impossible that there could be any way for him to win. It turns out that it's true. He can win if he's smart enough. Here's something more surprising. He wins even if he's stupid. Okay? No matter how stupid he is. Okay? If he, at every stage, picks a head completely randomly, He is guaranteed to eventually win. Takes a long time. For a moderately complicated 5-headed hydra, takes about that many steps. That's a 10 with 134 million zeros after it. To put that in perspective, the number of seconds that have passed since the Big Bang is 10 to the 17. The number of particles in the universe is 10 to the 86. And the mathematician J.E. Littlewood once, for some reason, asked this question: how many mice would you have to send to the surface of the sun in order for one of them to, by incredible good fortune, survive for a week? And the answer to that is 10 to the 137, considerably more than the number of particles in the universe, but far, far less than the amount of time that it takes for Hercules to beat the Hydra. In fact, if you sent a mouse to the moon every time Hercules cut off a head, then some fantastic number of them would survive a full week before Hercules got around to winning this game, but he eventually wins. So, fact 1, Hercules wins if he's smart. Fact 2, he wins if he's stupid, even though it takes a long time. And here's fact 3, the most surprising of all. Even though facts 1 and 2 are true, and even though they are facts about arithmetic, I expressed this all in terms of hydras, but this is really all arithmetic in disguise. Fact 2 is true, but it cannot be proven from the usual axioms of arithmetic. There's a concrete example of a true statement about arithmetic that can't be proven from the usual axioms. Well, if it can't be proven, how do I know it's true? I know it's true because a couple of guys named Paris and Kirby proved it. Proved it how? They said, well, the axioms that we have aren't enough. We'll add a new axiom. Just as Achilles did when he was fighting with the tortoise. We add a new axiom, which is perfectly safe to do as long as we're sure that the new axiom we add is true. The axiom they added was, the piano axioms are consistent. The piano axioms themselves cannot prove that the piano axioms are consistent. To say that they're consistent means that it's impossible to derive a contradiction from. This is an additional axiom, that the piano axioms are consistent. Kirby and Paris said, that's not on our standard list of axioms, but we don't care if it's on some standard list of axioms. We only care if it's true. And we know it's true because the piano axioms are true statements about the natural numbers, and a bunch of true statements cannot contradict themselves. Just because we know that a bunch of true statements can't contradict themselves, we know these things are consistent. So that's a perfectly safe extra axiom to add. Theory 1 is piano arithmetic. Theory 2 is the theory that Kirby and Paris used. They added another axiom. Theory 1 is consistent. Now you can write down new statements that are true but not provable from this theory. So you add another axiom, which says theory 2 is consistent. You can add another one that says theory 3. And the more axioms you add, the more things you can prove, but you never get to a point where you can prove all the true statements of arithmetic. That's Gödel's theorem. Nobody cares which axioms you're using as long as they're true. And that is most dramatically illustrated, I think, by this statement. Some of you might be familiar with this. It's called Fermat's last theorem. For 400 years, until quite recently, it was considered the most challenging and famous problem in all of mathematics to prove whenever you've got an equation like that, one of a couple things has to be true. Either n is less than 3 or x or y is 0. Here's an equation of that form up there, and sure enough, you can see that n in this equation is 2. It's less than 3. These are 3 of the people who jointly solved this problem: Gerhard Frey, Ken Rivett, Andrew Wiles. It was considered one of the great mathematical breakthroughs of the century, one of the great mathematical breakthroughs maybe of the millennium. And everybody sat up and said, this is fantastic. These guys have solved Fermat's last theorem. They've proved this statement about the natural numbers. But as far as I know, and my knowledge could be out of date, as far as I know, nobody has any idea whether Fermat's theorem follows from the Peano axioms, the standard axioms for the natural numbers. Because these guys did not restrict themselves to the Peano axioms. They used all kinds of stuff that you can't get out of the Peano axioms. They used, for starters, the very existence of the real numbers, which the Peano axioms can't even talk about. They used the existence of enormous infinities. They used the existence of set theory. They used the consistency of set theory. Fantastic amounts of stuff that the Peano axioms can't talk about in order to prove a statement about ordinary arithmetic. And again, mathematicians in practice use anything that's true. They don't worry about whether it's on some preset list of axioms. Why have I gone down this path? Because the whole point is that mathematics is about discovering true things about the natural numbers. It's not just a game with axioms. And if it's about discovering true things about the natural numbers, that presupposes the existence of the natural numbers. Coming back to the topic I really want to talk about, the natural numbers exist in the same sense that the Wisconsin state capital does and the unicorn doesn't. Mathematicians, there are thousands and thousands of quotes from famous mathematicians saying basically the same thing. This is G.H. Hardy, one of the great mathematicians of the early part of the 20th century. Mathematical reality lies outside us. 317 is prime not because we think it's so, but because mathematical reality is built that way. David Mumford, one of the great mathematicians of the last part of the 20th century. The more you study mathematical constructions, the more you come to believe in their objective and prior existence. Now, the fact that these guys said that doesn't make it so. But I do think, as a general rule, that if you want to know what Greenland is like, it's probably best to start by talking to people who've spent a lot of time in Greenland. And if you want to know what mathematical objects are like, it's probably best to start by talking to people who've spent a lot of time studying mathematical objects. Almost all of those people will say the same sorts of things we just saw on the screen. They'll say that there is a truth of the matter about Hercules and the Hydra. Either he always wins, and even if you don't believe anything I said about Hercules always winning, I'm not asking you to believe that. I'm only asking you to believe that either he always wins or he doesn't always win, that there is a truth of the matter, that there is a truth of the matter about Fermat's theorem. Once you've got the natural numbers, you also have all of the intricate patterns that live inside the natural numbers. Very simple patterns, like the pattern of even numbers, odd, even, odd, even, odd, even, or incredibly intricate, like the pattern of the prime numbers. I put the prime numbers in red there. There are hundreds of people alive today devoting their lives to teasing out the details of that incredibly intricate pattern of the prime numbers. As intricate a pattern as anything we know. It's certainly far more intricate than the pattern of a whale's brain. So if I have made some stab at convincing you that mathematical objects exist, my next step is to ask what else exists. And you might say, well, rocks, trees, spiders, light, my consciousness, possibly your consciousness, the universe itself. But what are those things? What's light? If you ask the physicists, they'll tell you that light is a disturbance in the electromagnetic field. What's the electromagnetic field? Well, if you pick up a freshman textbook, it'll say something like it's a function that takes as input a time and a location, and it gives you out 6 numbers. A more advanced textbook will have a more advanced description. But the electromagnetic field in any physics textbook is always described as a purely mathematical object. And light is a disturbance in that purely mathematical object. What are rocks and trees and spiders? They're made of atoms. Atoms are disturbances in a quantum field. What's a quantum field? Again, I could have picked from any of dozens of textbooks. This was a random one I pulled off my shelf. A quantum field is well, I don't have to read that to you for you to see that it's a very mathematical description. What is consciousness? It's a pattern. It's a pattern of connections among neurons and synapses, which are made out of atoms, which are made out of quantum fields. What's the universe itself? Pick up a physics textbook. And when I say the universe, I don't just mean the universe at this moment. I mean the universe together with its entire history. The physics textbooks will tell you it's something like a four-dimensional manifold with a Lorentz metric, and then lots and lots of other extra bells and whistles added onto that. None of that is meant to be literal truth. What physicists mean when they say the universe is a four-dimensional manifold or a 26-dimensional manifold is something like this. Some properties of our universe are well approximated by the properties of these simple mathematical objects. As physics progresses, we hope to find other mathematical objects that yield even better approximations, but as we go over time to the more and more sophisticated descriptions, they remain purely mathematical, and I don't know of any conceivable alternative on the horizon. When I look at you, you don't look like you're made out of math, but you also don't look like you're made out of atoms. Okay? We know that our perceptions do not reveal the base level of reality out in the world. Even if I could see the atoms inside you, I would not see that those atoms are actually disturbances in quantum fields. If I could see the quantum fields, I might not be able to see that they are purely mathematical objects, but the fact is that nobody has ever found any description of them that is anything other than a mathematical object. The only alternative to that story, the story that everything is ultimately math, is to say that the universe is made of some mysterious something else that happens to behave a lot like mathematical objects, that happens to behave a lot like those mathematically described quantum fields that the textbooks tell us about. And God knows what it is. So what you've just done is you've added to your metaphysics a mysterious thing which you can't describe in any way and adds absolutely nothing to your ability to actually describe anything or make any predictions. It adds nothing to our predictive powers. Here are two people who I think would have objected to that. One is William of Ockham, who told us don't multiply entities unnecessarily. In other words, don't pretend that there is something else that the universe is made out of if you don't have to. And Bertrand Russell, who told you not to believe anything without a reason. Well, I have no reason to believe that there is any substance other than the substance of pure mathematics. That's Max Tegmark. He is the physicist at MIT who is most associated with this general way of looking at things. He has what he calls the mathematical universe hypothesis. It's not verbatim the same as the argument I'm trying to make today, but it's very, very close. And again, the fundamental idea is that because mathematical objects exist, nothing else has to. Mathematical objects do exist. Some of those mathematical objects are complicated in some of them are very simple. Some are so complicated that they contain in them sub-objects that are complicated in just the right way to be aware of themselves. Those are you and me. Our universe happens to be one of those objects that is so complicated that it contains within itself self-aware sub-objects. There are presumably others. In fact, we know there are other universes because some of them are so simple we can write them down. This is Minkowski space. If you've ever studied relativity, it's the first space you study in relativity. It's a self-contained universe. You can write down a complete description of it. It's a very simple world. It has no matter. It has no electromagnetism. It has no gravity. It just has space and time. There it is. You can write down a full description. Of course it exists. I've seen it written down. A more complicated space is the Gödel universe. This is the same Gödel we met before, although this work is entirely unrelated to his earlier work. Gödel showed that it's possible to write down a full mathematical description of a universe like ours in some respects, except that when you live your life in this universe, you eventually keep coming back to the same time and place. So you keep merging with your own younger self. And does that universe exist? Yes, it's a purely mathematical object. He wrote it down. It exists. Are there living, breathing, thinking creatures in it? Surely not. It's not complicated enough for that. If it were more complicated, maybe there would be. This is Father Guido Sarducci, who used to be a regular on Saturday Night Live, and he used to do he described his travels to another universe that was exactly like the universe that we live in, except in that universe, people hold their corn on the cob vertically when they eat it. Does that universe exist? I want to say if our universe exists as a mathematical object and all I got to do is tweak an equation here and there to make the Sarducci universe, yeah, then that probably exists too. Maybe not. Maybe those little tweaks of the equations end up introducing inconsistencies that I don't know about. But I'm guessing that that universe is as real as ours. All these universes exist mathematically. You can write them down. Do they also exist physically? What's the difference? Okay? What would it mean to say that some exist physically and others exist only mathematically? Again, I don't even know what that means. I don't see how to draw that distinction. I don't see any purpose in trying to draw that distinction. And raising the question sounds to me suspiciously like every other failed argument that tried to argue that, the Earth is somehow special, it's the center of the universe. Humans are somehow special. We were created by God. Our universe is somehow special. It's the only one that has physical existence. The others are out there. We know they are. We can write them down. Why would they be any less likely to exist than ours? This guy, Copernicus, would be, I think, the first to tell you that it's often a mistake to think that the environment we're used to is somehow more special than the other environments we can imagine. That leaves me with this. Here's me talking. And again, I don't know that any of this is true. It could be complete nonsense. I want to claim it's plausible, and I want to claim I have no better story. And I want to claim I've never met anybody else with a better story. I hope someday I do. But I want to say this, the universe exists because it's made of math. Math exists because it must exist by its very nature. We didn't really get much time to talk about that point. I would have made that point if we had more time. All of this is confirmed by my direct experience. I know math exists because I live with it. And understanding all that makes me feel intellectually fulfilled. But then I imagine this religious guy who somehow showed up here by mistake. And he wants to say, the universe exists because it was made by God. And God exists because he must exist by his very nature. And that's confirmed by my direct experience of God. He talks to me, right? All right. That's Revelations. And understanding this makes this religious guy feel intellectually fulfilled. And when I look at the parallelism there, it makes me very uncomfortable because I know that guy's wrong. And I think I'm right. I think I might be right. But the parallelism disturbs me. Now, I think there are important differences between us. For example, the notion of the natural numbers is very precise. Everybody who has ever studied the natural numbers agrees on what their properties are. Euclid knew that there were infinitely many primes. I know there are infinitely many primes. We know it for the same reason. The notion of God is a lot more vague. It's a lot more... Everybody who talks about God seems to have a somewhat different conception of what God is. It seems more vague. It seems more distant. Okay? That's like an important difference here. Another important difference is that throughout history, pretty much everybody who has trusted math for anything has made better predictions than anybody who has ever trusted God for anything. Okay? And I think that's important too as a difference here. And yet the parallelisms remain, and the parallelisms make me a little bit uncomfortable. And having expressed that discomfort, I am done. Sure.
All right, some questions.
So I used to have a similar view of mathematics and mathematical objects at sort of the mathematical universe. The concern about this that I couldn't really overcome is, what do you mean by mathematics or mathematical object? Because it seems that if we use a sufficiently expansive definition that essentially all objects are mathematical, then the word has become empty. We're essentially using mathematical object to mean object. So I guess my question is, how do you overcome this concern? How do you use mathematical object in a sufficiently general way for this argument to go through, but in a precise enough way that it isn't just a, empty property?
This is the huge problem. I'm not even sure which mathematical objects I want to really claim the existence of. The natural numbers, I feel like I'm on very solid ground, that I know that there is what a mathematician would call a standard model of the natural numbers, and that's the one place where I feel confident that I'm talking about something that I want to assert the existence of. It might be enough, because within the natural numbers, there are embedded patterns. Certainly, your entire brain can be modeled as a pattern within the natural numbers. That might be all we need. Something like the real numbers, is there a standard model of the real numbers? I have no idea. Is there a standard model of Zermelo-Fraenkel set theory? I don't even know how to think productively about that. I'm not sure how far beyond the natural numbers I would be comfortable going. I'm not sure how far beyond the natural numbers I need to go. Tegmark has written a lot about this. He has these ideas of computable mathematical structures, which he believes is the key to answering your question. I cannot make sense of what he's talking about when I read those papers. And I hesitate to say that the papers are confused or wrong, because he's a lot smarter than I am, and he's thought about this a lot more than I have. But his approach does not seem to me to be working. Probably that's because I don't understand it well enough. But there is definitely a huge problem on drawing the line on this kind of thing. Yes. Well, I'm not a cosmologist, so I cannot tell you all the ways that cosmologists use the notion of information. Certainly, modern proofs of Gödel's theorem are based entirely on this notion of information. In fact, I had a couple of slides. I can give you a complete proof of Gödel's theorem in about 2 slides, but I didn't want to go over my time. The answer, the best answer I can give in the amount of time I'm willing to take is that the question of what axiom systems can and cannot accomplish, and the question of how to model information are very intricately linked, and there's a lot of papers where ideas from those 2 areas fertilize each other.
In the study of fundamental physics, there's something called group theory related to symmetry theory. And there's particular manifestations of particular groups that are relevant to the description, a mathematical description, of some of the fundamental forces of nature. The double cover of the Poincare group, right? And the interesting point to me is that there are many, many other mathematical groups that, so far as we know, have no relevance to physical structures or interactions. It seems like it's a bit of an extreme form of Platonism to say the mathematics is the real thing instead of the underlying physical processes and entities are the real things. And in many cases, there's a one-to-one mapping between those things and a mathematical description. But it's not, both sets are not completely covering each other. There's far more mathematics than there is physical manifestations. And it may be that the Venn diagram leaves out some physical processes that we don't have a logical mathematical mapping.
But what I would want to say is that, you can write down the Lagrangian for our universe, and there are groups acting on that. You can write down another Lagrangian for some other universe, and there are other groups acting on that. And that our universe is not special, right? That our universe happens to have the Lagrangian it does. Some other universe happens to have a different Lagrangian. Some groups are relevant for one. Some groups are relevant for another. That anything that exists, my slogan is that if it exists mathematically, it exists physically. It doesn't mean it exists in our universe. The Wisconsin State Capitol exists even though it doesn't exist in Pennsylvania. The natural numbers exist even though they don't exist in our universe. Some representations of some groups have some manifestations in some universes that they might not have in our universe. I agree that our universe has a lot of very specific properties that make it distinct from others. But I would want to argue that there's no reason to think that it is somehow special as compared to those others.
All right, thank you, Stephen. Can we have one more round of applause from him, please?